Good afternoon, my name is Daniel Perez, and in this lab, we investigated the acceleration of a cart moving on an inclined plane. The objective was to compare the experimental acceleration obtained from the velocity versus time graphs with our theoretical acceleration. In the first part of the experiment, we used a motion sensor to record the cart's position over time. From this data, we created a velocity versus time graph and determined the acceleration from the slope of that graph. We then compared this experimental value with the theoretical acceleration calculated using measurements of the incline of the track. The next thing we did was we changed the mass of the cart by adding additional weights while keeping the incline the same. Our results showed that the acceleration value stayed very similar after adding the mass. After that, we changed the tilt of the track by adjusting the height of the slabs under the air track. Changing the incline changed the acceleration of the cart. When the track was steeper, the cart accelerated quickly. This showed that the angle of the incline played an important role in determining how fast the cart was speeding up. So some real-world applications for this would be the designing of roads, ramps, or even roller coasters, transportation systems as well. Engineers commonly use these principles to determine safe slope angles and predict how vehicles or objects will accelerate when moving downhill. And that's it. Thank you.
So these are our materials. We have two 100-gram weights, two silver weights, a ruler, and we have this glide that we're going to be used to measuring the weights on a ramp. Then we have the motion detector, which is going to give us our graphs. We're using a laptop for instructions and a calculator to help us with our calculations.
Now. Right now, we're just trying to get the motion sensor to be calibrated to the height, and right now we're having a little bit of trouble.
Yeah.
Uh-oh.
This is not working.
Maybe.
Try it again.
It's just going to be a U-shaped graph.
U-shaped graph? What are we getting a U? Oh. Like a U or like an upside down U?
It says it on the instructions.
Getting a U-shaped graph.
Just do a test again to see how it's looking.
Yeah, try it.
Yeah.
Alright. I have my finger over here, so we'll stop.
Yeah.
Alright, ready?
Yeah. Go. Oh, okay. Now it looks like it was working.
Yeah, but the only way to get a U is it has to slow down. Like it has to go, or it has to like start really slow and then speed up. I don't know how we're getting the U. I don't know, maybe when it hits the...
Like the skin and it bounces back.
Yeah.
But we don't need that for... Ready?
that little dip.
Yeah, I don't know. Maybe it loses like track of it or something like that.
Maybe. Wouldn't it be the very top one?
Yeah, we can do that.
First one. Yeah, first one.
Oh yeah. Same thing here. So I'm gonna label this. So this is for the.
This one also took longer to accelerate.
If I'm correct, it shouldn't be like a huge difference.
Oh, I think it's like 0.5 seconds more.
0.4. Percent there, or what? Or are we supposed to do theoretical? I mean, I guess it won't affect it because we have a good beginning and end.
Yeah,
Right.
I'm assuming we just use that first line because that's the fastest line.
Yeah, and then the end over here.
No, I'm assuming we use the very top.
Well, it's just like, look at this right here.
Yeah, I see what you mean.
So just like right here.
Yeah. Oh, you put the wrong one.
The wrong one?
No, not the wrong one. Like you pushed the wrong option.
Oh.
Yeah, just delete it.
It's like a ski
Push on the X. Push on the X. It's the first one.
This one? Yeah. And then the next one, which is, I guess it's gonna be this one.
Oh, I thought we were using like the very first one. Like,
I guess. Okay. So there's equals 0 for initial, or no, actually.
0.06.
Yeah, right.
Yeah.
That's good. 0 minus, what's the top one?
Top one.
0.93.
1.93.
Okay.
Then it'll be 0 for initial time.
0.
2.8 seconds.
So using the sine, finding the sine which is opposite over hypotenuse, we got 3 centimeters for our opposite and 100 for our hypotenuse. We divided them 0.0, and we got 0.03. Multiply that by the gravity, 9.8. We got 0.29 meters per second. This would be our theoretical acceleration.
Hello, my name is Angel Ortiz, and I'll be going over our data and conclusion for this lab. So for this lab, we first calculated a theoretical acceleration, which was 0.29 meters per second. Then for our first test, which had low mass and high tilt, we got an acceleration of 0.33 meters per second, which compared to our theoretical acceleration is a 12% difference. And then for test 2, we had high mass, high tilt, which had an acceleration of 0.34 meters per second and a 12% error difference between our theoretical acceleration. Then for test 3, we had high mass, low tilt, and we expected it to be 0.15 meters per second, and our actual acceleration was 0.19 meters per second. And the percent error between test 1 and 2's acceleration was around a 3% difference. Now, in this lab, were we expecting different accelerations? Yes, because we had different variables. One test had low mass, high tilt, one had high tilt, high mass, and the other one had high mass, low tilt. So the one we expected to be higher would be the one with a high tilt and higher mass because there's more energy behind it moving. We were not really expecting a different error percent than what we got. It was within range of what we thought of 10 to 15%. We were these results that we got, I feel, are pretty accurate because it wasn't a major percent difference between any of our experiments. All of them were within 20%, which I feel like is pretty good. Obviously, we would want it to be lower than 10%. The accelerations were different because, like I said again, there were different variables between all of the experiments, so we should have had different variables. Our percent errors were roughly the same. For experiment 1, our percent error was 12%, and for experiment 2, the percent error was 14%, so they're roughly the same. Our experiment with the more significant error percent was experiment 2 because it had a higher percent it had a 14% error, while experiment 1 had a 12% error. And our test with the most unexpected value would be test 2 in our opinion, because we thought it would be faster than what it was because it had more mass behind it, but it wasn't really all that different.